The Earth is a vast, spinning orb of partially molten rock with a heart of iron that burns as fiercely as the surface of the sun. Beneath our feet, immense heat, ancient energy left over from the planet's fiery birth, and the radioactive decay of trillions of tons of radioactive elements has no escape. It churns relentlessly, traveling in colossal currents through the mantle, spanning thousands of kilometers, eventually brushing against the base of the crust. The crust is the planet's only barrier, a thin, fragile shell that appears solid to us, but is more like the delicate skin of an apple enveloping a slumbering giant. This barrier can crack, and when it does, the consequences are apocalyptic. Eruptions tens of times stronger than all the nuclear weapons ever detonated, capable of reshaping climate systems in a single year and covering continents in suffocating clouds of ash and poisonous gases. These are the terrifying potentialities of supervolcanoes. How large can they grow, and could they truly threaten humanity? Volcanoes come in a staggering variety of forms, from massive stratovolcanoes that pierce the sky to low, dome-shaped mounds that ooze lava slowly over centuries. Despite their diversity, all volcanoes originate from just two primary processes. The first occurs at the boundaries of tectonic plates, the vast slabs of Earth's crust that float atop the molten mantle like puzzle pieces drifting atop an invisible ocean. There are 7 major plates and dozens of smaller ones, moving at rates up to 15 centimeters per year. To us, this seems glacial, but over geological time, it is an epic struggle for supremacy. When one plate dominates, it may crumple into towering mountain ranges, while the vanquished plate is pushed beneath the surface into a fiery abyss known as the asthenosphere. Temperatures here reach around 1,300 degrees Celsius, hot enough to liquefy rock, yet the immense pressure from overlying layers keeps it in a superheated solid state. Plates carry water absorbed over millions of years from oceans and sedimentary layers. When they descend into the mantle, this water triggers chemical transformations, lowering the melting point of surrounding rock and forming pockets of magma. Being less dense than the surrounding solid rock, this molten material rises through the mantle in furious, buoyant plumes, collecting in vast sponge-like reservoirs beneath the crust. When enough magma accumulates, the pressure becomes intolerable. The molten rock forces its way through the crust, erupting violently at the surface Often these eruptions occur beneath the winning plate, a kind of vengeful strike by the losing plate before it is fully consumed. These processes have sculpted the world's most dramatic landscapes, from the Andes in South America to the fiery peaks of the Ring of Fire encircling the Pacific Ocean. The second source of volcanic activity comes from mantle plumes, columns of abnormally hot rock that rise from the core mantle boundary to the surface. These plumes are poorly understood, but scientists imagine them as the Earth's internal weather, vast, slow-moving storms. Of molten rock, rising at only a few millimeters per month, they are oblivious to the motion of tectonic plates. They can puncture the crust in the middle of tectonic plates, forming volcanoes in seemingly random locations that stubbornly remain active as the crust drifts around them. Examples include Iceland's volcanic systems and the massive Hawaiian Islands, created over millions of years by a single mantle plume. Scientists quantify eruptions with the Volcanic Explosivity Index, or VEI, a logarithmic scale measuring the volume of material ejected. It begins modestly but escalates rapidly. A VEI-2 eruption produces enough lava to fill roughly 400 Olympic-sized swimming pools, and around 10 of these occur every year. At VEI-3, eruptions are already destructive. The 2021 eruption of Mount Semeru in Indonesia, for instance, devastated thousands of homes and displaced tens of thousands of people. V5 eruptions are catastrophic, hurling cubic kilometers of molten rock and ash skyward, as exemplified by the 2022 Hunga Tonga Hunga Hapai eruption, which sent shockwaves around the globe multiple times and generated massive ocean-wide tsunamis. V6 eruptions have the power to alter the planet. In 1883, Krakatoa erupted almost continuously for 5 months. One colossal explosion obliterated the island, producing the loudest sound ever recorded, 10 trillion times louder than a rocket launch, and audible halfway around the world. Tsunamis over 30 meters high swept away entire coastal settlements, and the enormous clouds of ash and gas cooled global temperatures by nearly 0.5 degrees Celsius. Dust-laden skies produced red sunsets that lingered for years. These 7 eruptions are truly monumental, events that redefine human history. Mount Tambora, 4,300 meters high, erupted in 1815 with a force 400 times greater than the energy released by the atomic bomb dropped on Hiroshima. Approximately 140 billion tons of ash and dust were blasted halfway into space, turning skies a sickly yellow. The following year became known as the year without a summer. Crops failed, and over 100,000 people perished worldwide. These events demonstrate the frightening potential of volcanic eruptions, causing widespread famine, climate disruption, and decades-long cold spells. The term supervolcano is largely a media invention, but the phenomena behind it are real and terrifying. Not every eruption from one of these giants is cataclysmic, but their unique characteristic is the enormous pressure that builds over hundreds of thousands of years in colossal magma reservoirs kilometers beneath the surface. The weight of rock above, combined with the slowly accumulating magma, eventually fractures the crust. When this pressure is finally released, billions of tons of gas, ash, and molten rock erupt at supersonic speeds, ejecting at least 1,000 cubic kilometers of material into the atmosphere. Even then, this is only a fraction of the total magma reservoir. A super eruption is like a boiling pot, violently spewing some of its contents, followed by the collapse of the ground into the void, forming a caldera. Over millennia, pressure rebuilds beneath the caldera, potentially triggering another super eruption hundreds of thousands of years later. One of the few supervolcanoes capable of this is Yellowstone in the United States, which is estimated to produce catastrophic eruptions roughly every 177,000 years, far more frequent than asteroid impacts of comparable destructive potential. The most recent super eruption, the Oroonui eruption in New Zealand 26,500 years ago, released the equivalent of billions of tons of TNT. A vast portion of the landscape was hurled skyward, leaving a caldera 20 kilometers across, and causing abrupt cooling across the southern hemisphere. A more significant event, the Toba eruption 74,000 years ago, expelled 5,300 cubic kilometers of material. This deposited ash across much of South Asia, caused a global temperature drop of roughly 4 degrees Celsius, and may have triggered a volcanic winter lasting a decade, followed by worldwide droughts for centuries. Some scientists suggest that Earth's climate did not fully recover for 1,000 years. The largest volcanic events ever recorded were not violent explosions, but continuous outpourings of lava, flood basalts, covering millions of cubic kilometers of land. The Siberian traps, around 250 million years ago, released lava for 2 million years, raising ocean temperatures to over 40 degrees Celsius, and triggering the Permian-Triassic extinction, which wiped out over 90% of species. These eruptions didn't merely change the climate, they were the climate itself. Thankfully, nothing of this magnitude has occurred for millions of years. So, should you fear supervolcanoes? The short answer, no. Supervolcanoes have been sensationalized. Yellowstone, for example, will erupt again, but the likely eruptions are much smaller than a true super eruption. The probability of a VEI-8 eruption in the next few hundred years is under 2%. And even then, the warning signs are clear: ground swelling, increasing temperatures, changes in gas emissions, and minor seismic activity would alert us long before a catastrophic event. Meanwhile, smaller, more frequent, or eruptions remain a significant hazard, capable of devastating populations and economies. Monitoring magma chambers is critical. Measuring ground deformation, heat flow, and gas emissions can give early warnings that save lives. Furthermore, humans are developing strategies to mitigate the climate effects of eruptions, such as filtering sulfur and ash from the stratosphere or capturing geothermal energy from magma reservoirs. The same ingenuity that allows us to deflect asteroids or probe distant planets may one day turn these destructive forces into a source of energy and benefit. So while deep beneath our feet the Earth's molten heart churns and waits, plotting its next violent display, humanity can rest easy. Science, technology, and vigilance ensure that even in the face of immense geological power, we are prepared, resilient, and ready to turn potential disaster into opportunity.